Hi everyone, I'm Roshan Sahu. Today we will be performing a simulation. As you can see on the screen, this is our question. Today I'll be teaching you how you can perform a simulation given some of the data that has been provided to us is incorrect. So, looking at the question, use the shortcut features of the HeatX block to calculate the state of the cold stream and the heat transfer area required when the streams in the table are passed through a countercurrent heat exchanger with an overall heat transfer coefficient of 100 BTU per hour per feet square degree Rankine. The outlet temperature desired for the hot stream is 70 degrees Fahrenheit. The temperatures of the hot and cold feeds are 140 and 40 degrees Fahrenheit respectively. Both streams are at 14.696 psi. Use the Wilson property method. So, without much further ado, let's start Aspen. The components that we have today are, the first is methanol, water and glycol. The property method has already been specified. We will be choosing the Wilson method. Right? Now we click on next. We can click on next. It's the property analysis setup will be run right now. It's processing the input specification. Okay, some computational difficulties might occur. Okay, table generation is complete. Now we move on to the simulation tab. We'll be using the heat exchanger that is under exchangers, the HeatX model. We'll be using this. We click it on the screen. We add the material streams after that. By convention, the hot material will be passed through the tubes and the cold one through the shell. Right. We rename the streams for, easier understandability. That is hot in, hot out, cold in and cold out. The model is HeatX. We place it conveniently. Not stuck. Now we enter the stream data. We need to enter the data for cold in and hot in. As you can see, there's a red mark near each of them. So we have to compulsorily give the data for them. Temperature of the cold stream, we will first change the unit sets to English. The temperature of the cold inlet stream is 40 degrees Fahrenheit and the pressure is 14.696. It's psi. The flow rate of glycol in the cold stream. Glycol is a coolant. The flow rate is given as 400. It's in mass flow, so it's 400 lbs per hour. For the hot inlet stream, the temperature is 140 degrees Fahrenheit. The pressure is 14.696 psi. And the flow rates of methanol and water are, we'll first change it to mass flow rate. The flow rates of methanol and water are 200 and 1800 lbs per hour respectively. Now we move on to the blocks. We've got the HeatX as our only block. Let's look at the question. It says that we have to, the outlet temperature, the outlet temperature desired for the hot stream is 70 degrees Fahrenheit. So that is what we have to specify out here. Hot stream outlet temperature 70 degrees Fahrenheit. Right. And the total heat transfer coefficient, the overall heat transfer coefficient is given as 100 BTU per hour per feet square degree Rankine. We also have to enter that here under the U methods. We take a constant U value of 100 BTU per hour. Now we click on next. All the required input is complete. I'd run the simulation now. Now we see errors have crept up. Two errors have crept up, and the error is temperature crossover has been detected. This means that the temperature of the cold stream, the inlet temperature of the cold stream is higher than the outlet temperature of the hot stream. So that should not happen ideally. So we will reinitialize the simulation first and proceed to correct it by trial and error method. So how can we do that? By normal logic, you know that if we increase the amount of the coolant, the flow rate of the coolant, then temperature crossover might not occur. So cold stream inlet from 400, let's change it to 4000. Right, just as a wild guess. I again press next, run the simulation. Yeah, it executed. You can see it's blue right now. But we do not want to waste any coolant because obviously, right, you know, they are expensive. You cannot waste them. So in an ideal situation, we need to optimize this. This optimization will be carried out by trial and error method. So now I'll again change the cold stream inlet from 4000 to, let's say, 2500. Right. Now I'll again press next and run the simulation. No inputs, no errors, there was only one warning. Right. Okay, so it is definitely below 2500. I'll reinitialize the simulation again. Right, and go to the cold stream input. So it's something below 2500. Let's take it to 1900. I'll press next and run the simulation. No, it's not executing. So move back, initialize the simulation, and input I'll be changing it to 2000. I press next and run the simulation again. Still it's not working, so it's in between 2000 and 2500. So I'll again reinitialize the simulation. Input I'll keep it at 2400. Press next. Yeah, it worked. At 2400 it worked. So I'll reinitialize the simulation again. Input I'll be changing it to 2300. Okay, so it doesn't work at 2300, so that means 2400 is actually the ideal flow rate of glycol. So I'll check it again with 2400. Next. Okay. Yeah. So now we can move forward and view the results. Let's see what the question asks of us. The question asks of us to calculate the state of the cold stream and the heat transfer area required. Right. So the state of the cold stream can be found out from the cold results, the cold output, we view the results. This is the result of the cold stream, the total flow rate and everything.